All right, welcome to another exciting episode of AP Chemistry here at Spain Park. Today is Friday, November the 1st. It is already November. We're almost halfway through the first 9 weeks.
Thank you,
Unbelievable. Okay. I mean, first semester. First semester. See that? Time's flying so fast I can't even keep up. Okay, first semester. Okay, so we do have a test on Monday. So I want to spend today just kind of reviewing, okay, just for the first few minutes, some of the key points that I want to make sure that you understand. Number one, we did a lot with electron configurations and arrow diagrams. So when we do an arrow diagram or an electron configuration, it's just kind of easier to understand 1s, 2s, 2p, 3s, 3p, 4s, then 3D, okay? There are 3 rules for filling this. Number 1, we have the Aufbau principle. That's it. Come on, Steve. A-U-F-B-A-U, okay? Aufbau principle. Simply means you start at the lowest energy. This is increasing energy, not distance. So we start at the bottom and work our way up. We don't go to the 2p until the 2s is filled. We don't go to the 3p until the 3s is filled. Okay? When that happens, when you satisfy the Aufbau principle, and this is all in those notes that I gave you. Okay? When you satisfy the Aufbau principle, it's near the end of the notes. Okay? You start at the bottom. Lowest energy first. Now, does anybody, why is 4s come before 3d?
Because it's earlier.
I know, but why?
More protons.
No, that's generally a good guess though. Okay, so here's your 4s electron out here, and you have your 3d electrons here. Here's your nucleus. Why is this one being held more tightly? Well, remember, lower energy means held more tightly. Why is the 4s held more tightly than 3d?
It's being shielded less.
Well, but the 3, it's actually 4s. If it's out here, it's going to be shielded by all of these. But it.
Less repulsion.
Mm-hmm.
Because it just is.
Nobody remembers my whole discussion on that?
I just remember you telling us it was. I don't remember you telling us.
Yeah.
Remember when we talk about the average distance away, that, okay, that most of the time it's going to be out here. But there's going to be a small but significant amount of time it's closer to the nucleus. So in other words, it's going to come in some of the time, it's going to penetrate in closer to the nucleus. So Coulomb's law, the closer you get to the nucleus, what does that mean about attractive force? Stronger. So because even these two are going to be very close in energy, 4s and 3d. There's not much difference in energy to start with. And then the small but significant amount of time it can get closer in, because it takes a different path, it's a different type of wave function than the 3D, it's actually held more tightly, even though the majority of the time it's farther away from the nucleus. The small but significant amount of time it gets closer in actually causes it to be held more tightly, which means it's going to be a lower energy, so it's going to fill first. Okay? So the Aufbau principle says you fill the lowest energy levels, the ones that are held the most tightly first, which is why 4s comes before 3d. Okay, so that's the first principle. The second principle is Hund's rule. And what does Hund's rule say?
Oh, it's like
Same span.
they all fill up and then
Okay, so we're going to go 1, 2, 3, 4. Let's look at oxygen. 5, 6, 7. Then it begins to pair up at 8. Now, it's because of Hund's rule that we know that oxygen, or we can explain why oxygen is paramagnetic. What does paramagnetic mean?
Sometimes magnetic.
It's affected by magnetic field, right? And what must be true for something to be paramagnetic?
It has to
No. It has to have at least one unpaired electron. It's got to have the unpaired electrons, not both. Okay? So it's got to be unpaired. Well, if Hund's rule wasn't true and oxygen did that, then it wouldn't be paramagnetic. What would it be if it has no unpaired electrons?
Diamagnetic.
Ferro is the permanent magnet. Diamagnetic means there's no unpaired. What are the only three groups that are diamagnetic?
2, 12,
2, 12, and
18.
18. Okay? But because of Hund's rule, we know that oxygen and anything that has unpaired electrons would be paramagnetic.
So if you were like drawing something, if you were drawing a chart like that for the other, like not the diamagnetic ones, would you like not fill in those other ones?
Well, like again, you go to neon, it's gonna be like that. So neon has all paired electrons, so it's gonna be diamagnetic. If it's just going to be, so this neon would be family 18. Here, this is family 2. This is your beryllium. It's all filled. And then the end of the D sublevel, all the Ds are filled on family 12. Okay? So we have Hund's rule, and our magnetism is related then to Hund's rule. The whole idea that you have unpaired electrons. Otherwise, if Hund's rule wasn't true, they begin to pair up. It wouldn't necessarily be paramagnetic. Okay? Do you see how the two are related? Paramagnetics, unpaired electrons. Hund's rule says that you put one into each, which is why it's going to be paramagnetic. All right. And then lastly, we have Pauli exclusion principle. What does that say?
Spin.
They have to have opposite spins if they occupy the same.
How many Macs can be in there?
2.
2, and they have to have opposite spins. Okay? Why 2? Because there's only 2 possible spins. Okay, so if they had 3 different types of spins, maybe they could have 3, but there's only 2 different types of spins, and so 2 can only be in there.
What would you call each one of those lines?
Each of these? Okay, good question. We want to differentiate between 3 things: energy level, energy sublevel, orbital.
Yeah, that's a good idea.
We have the first, second, third, fourth energy level. On the second, well, let's just go to the third energy level. We have an S sublevel, we have a P sublevel, and we have a D sublevel. Okay? Now, on the S sublevel, there's only one orbital. On the P sublevel, there are 3 orbitals. On the D sublevel, there are how many orbitals?
10.
10 electrons, how many? 5 orbitals. Okay? So, energy level is the whole thing. That's the row on the periodic table. The S, P, D, and F are your sublevels. That's your sections on the periodic table. And each sublevel can have a varying number of orbitals. And they can, but no matter what, there can only be 2 electrons in any orbital. But because on the S sublevel there's only 1 orbital, you only have 2 electrons. On the P sublevel you have 3 orbitals, so you can have 6 total electrons. On the D sublevel you have 5 orbitals, so you can have 10 electrons. Okay, now who said that we can't know the exact position and energy of the electron?
Heisenberg.
That's the Heisenberg uncertainty principle, right? So we need to know these 3 plus Heisenberg uncertainty principle. And then who treated the electron like a wave and described everything in terms of wave?
Oh,
He had a pet cat.
Oh,
Schrodinger.
Schrodinger.
I was gonna say Hemingway.
No, not Hemingway. Wrong AP class.
We treated the bullet as what?
The electron is a wave. Schrodinger treated the electron like a wave.
I think it's in the notes somewhere.
It is. All right. Now, this, by the way, is what, whenever we draw our electron configurations, 1s2, 2s2, 2p6, in the normal way, that's always going to be called the ground state. Ground state means non-excited state, the lowest possible energy state.
Like not ionized, like not +2.
No, non-ionized is just the lowest energy state. In other words, there's no electrons up here without the electrons below it being filled. But what happens if I put heat or electricity onto this?
You do something with the electron.
The electrons can jump up, so I could move these electrons, say, up to here. So now this would be called an excited state. Okay? You got electrons in upper sublevels without the lower sublevels being completely filled. Go ahead.
Does it, like, when you do the energy like that and add energy and it jumps up, is there specific ones that it comes out of, or is it random? Like, does it only come out of 1s and then?
Well, most likely it'll come out of the higher ones because they're the ones that are least tightly held to start with.
So the ones.
But
that
if you
are-
put enough energy, you can knock them all, you can push them all up.
So like, if it had some 4s, but not.
Yeah, but you'll never have to know that. Okay? Because I have no way of knowing, I don't know the answer to that. I don't know how they, I would always assume that the farthest out ones are the least tightly held, so they would be the ones more likely to move up first. Now, they're naturally going to come back down, and when they come back down, how do they release their energy in the form of what?
Photon.
Photons, which could be light, but it could be infrared radiation, could be ultraviolet radiation, but they give it off in a photon with a specific energy. Okay? Now, what if I said something like 1s2, 2s2, 2p6, 2d5? Is that an excited state?
Super.
Wait, how do you have a 2D?
Because they jumped up there.
Okay? Say what? There is no 2D, right?
That's what I'm saying.
That's what you were saying exactly. So this is just impossible.
Okay.
Oh, great.
Okay.
Great job.
This is just impossible, okay? Because there's no such thing as a 2D. When's the first time you can have a D?
3.
On the 3. When's the first time you can have an F?
4.
4. So in other words, in order to have L equals 3, N has to equal at least 4 or higher.
I thought you were saying that
No,
the D didn't exist at all, and I was so.
no.
confused.
It's just, you can't have a D until the 3rd.
Yeah.
So this just won't never work.
So if it was like 4D5, would that be excited state?
If we went to 4D5, very good question, 4D5 like that, now that's possible, so that would be an excited state because you have electrons way up here in the 4D without the 3s, 3p, and all that being filled. Good question.
If it was a transition metal in the excited state, would it go from S to the 3D?
I don't know. It's just, I mean, you're asking kind of these crazy things. So, I mean, we're looking at a transition metal, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d something, okay? Now, you're saying go into excited state. Well, if we went 4s2, 4d10, now that's going to be an excited state.
Shouldn't the S come out first?
We didn't go S, we just pushed things up to a higher state. But yeah, I mean, but the whole thing is if you have electrons in a higher sublevel, doesn't matter which ones, okay, don't make it more complicated. If you have some in a higher without all the lower ones being filled, it's an excited state.
Oh,
Oh, wait, shouldn't the 4S2 come out?
Again, we're not making an ion. We're just promoting electrons. We're just filling, giving a potential electron configuration if you have electrons. Now, if I have 3d6, which would be, your 3d6 is going to be Fe. So if I go and make Fe3 plus, yes, it's going to come out of here and -1 out of there. So then I'm going to have 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Okay? But we're just talking for an excited state, just promoting electrons up, they come back down, we're not knocking them out and all that. So you just, if you have electrons in a higher sublevel without the lower ones being filled, it's called an excited state. That's what you do with heat and electricity. You just make the electrons go up, they come back down, give off photons in the form of light.
I just see like getting bigger things in the excited state. They skip both energy levels and sublevels.
Yeah, they just move up. The outbound principle is not satisfied. You got electrons up here without all of these ones below it being filled. That's all an excited state is. Okay, now the electrons will naturally come back down to the ground state. So you have to force them up with the heat or electricity. They'll naturally come back down, give off photons, which we see as light or other forms of electromagnetic radiation. That's how all light is produced. So what is fire?
Light,
And
heat,
heat as the result of
chemical reaction.
a chemical reaction occurs, gives off heat and light, so the surrounding air absorbs that. The electrons in the surrounding air go from a lower to a higher sublevel. They go to an excited state. When they come back down, they give off photons. Some of the photons are in infrared region, which we perceive as heat. Other of the photons are in the visible light spectrum, which we see as light. But it's all the photons in the area around because it's an exothermic reaction, so all the heat from the reaction is being given off to the surroundings being the air, the oxygen, the nitrogen, the gas that's being produced from the fire. Okay, all of those molecules there are the electrons then start going up, they come back down, they give off infrared, which is heat, they give off visible light, which is what we see. The hotter it is, the different photons, so it goes from yellow to blue and then to a white light as that gets hotter and hotter, so there's more and more excited photons and you get different color flames. Okay? So we can explain. So somebody's sitting around a bonfire, man, fire is so cool, man. What is fire? You can just go off into your little explanation and just, oh man, he's so smart. You know, hey, I tell you what, that's the way to get the ladies, guys.
I bet.
Not. But anyway. Anyway. So, excited state, ground state, impossible state. 2D is impossible. 3F is impossible. Okay? 1P is impossible. Okay? So we already did that. We did that. In terms of size, yes, sir.
On the test, will you make us write the electron configurations like in the way, the exact way, or are we just writing it out like you did right below that? Where
It's more going to be this.
are we going to have to at all go like?
I mean, AP doesn't ever make you do that. So this is what you need to know how to do.
Okay, I didn't know. What is it?
All right, our trends, shoot up here, please. Our trends, we know what happens as the atoms go down. What happens to them? They get bigger because,
More protons.
no,
More electrons.
more energy levels. Okay, more energy levels. What happens left to right in a period?
Smaller.
They get smaller,
Because of
more protons.
There we go.
However, notice that it's 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Your transition metals all tend to be nearly the same size because they all have the 4s out here, and then the 3d comes in a little bit closer. And then for every proton you add another electron, so the shielding kind of negates it. And so these all, there's not a big difference in size in your transition metals, okay? If we look on your periodic table on the back side, it's got the covalent radius up there, and it's 1.44, 1.32, 1.22, 1.18, 1.17, 1.17, 1.16, 1.15, 1.17. So they're all kind of staying the same size because of that. The 4s is all, they all have the 4s, and you're adding in the 3d on the interior. So transition metals tend to be the same size. Okay, there's not a big difference. All right, so that was something when we talked about the trends, I forgot to mention. And that's kind of an important, AP does ask questions about that sometimes.
They're not very different with their size.
That's their size. They stay relatively the same. Then when you go to the P, the trend kind of, and again, they're getting smaller, but they're still not getting all that much smaller. Just a little bit smaller.
It's not with mass, it's literally just with the size.
Yeah, yeah. Now, they are getting heavier too. I mean, the top of mass is increasing, but, okay? So just the ones that are gonna be closest in size are the ones that transition metals, okay? Least affected by that trend. All right, and then lastly, I'm just going through all of my different notes that I made to myself, okay? Electronegativity, we're actually gonna wait until bonding, because that's when we're gonna talk about it in the trend, okay? Now, but hey, listen, if it's no big deal. Fluorine's the highest, francium's the lowest, that's the trend, okay? So, I mean, highest electronegativity, and the most electronegative element, we already know that from phone call. Fluorine's the highest, top right are the most electronegative, bottom left are the least electronegative, okay? Now, we had to do, when an electron transitions, okay, when an electron transitions from the higher to the lower, it gives off energy in the form of photons. You went and did a whole bunch of practice problems on that worksheet on E equals h nu. Okay? What is E?
Energy of the electron, like to remove an electron.
No,
No.
the weight.
E is the energy of what?
The photon.
A photon.
Okay, not electron.
Okay? So an electron gets promoted up, and then it comes back down. It gives off a photon with a specific energy. E equals h nu. That's the energy of the photon. But it's one photon. One electron, one photon. So on that practice problem, does anybody have that sheet handy with those problems on it? Yeah. Okay, so number 5. A photon has a wavelength of 0.05 centimeters. First thing, what do we have to convert that to?
Nanometers.
Oh,
Meters. In all of that, it has to be meters. Okay? So when we calculate its energy, E is equal to hc over lambda, right? That was one of the equations on the bottom. Now, once again, that equation is not given. You're given E equals h nu and C equals lambda nu. Those are the two that are given on your equation sheet. Well, how do I get to this? Well, frequency is the common variable, right? So nu is equal to C over lambda. Just substitute it into here. E is equal to hc over lambda. That's how you get to that. Okay? Now you can do it in 2 steps, 1 step, but for the sake of time, let's do this in 1 step. So these constants are both given, 6.626 times 10 to the minus 34th joule seconds times 3.00 times 10 to the 8 meters per second divided by the wavelength. Change this, we have to 0.05, we're going to move it 2 more places, so there's going to be 3 zeros, meters. Okay?
Wait, 1, 2, 3, yeah.
Got 5 times 10 to the minus 4.
Okay.
Alright, what did we get as the answer?
3.98 times 10 to the negative 22nd.
Times 10 to the negative 22nd. Okay? And that's joules. So seconds cancel here, meters cancel there, leaving you joules. But that's joules per what?
Second.
It's just joules.
what is it the energy of?
Photons.
One
Joules
photon.
is that per?
That's per photon. Okay, now the photon's not really the unit, but it's per one electron transition per one photon. Whenever you're doing this equation, it's per one photon.
How would you write that? Would you write
You can say joules or you can say joules per photon.
Will we get it wrong if we don't put the per foot?
No, okay, but you're missing the point of where I'm going with this. Okay? A lot of times, especially in AP, it wants it in kilojoules per mole. Okay? Well, how do I change this to kilojoules per mole? Well, how do I change joules to kilojoules?
I don't even know what a kilojoule is.
So it's 1,000.
It's 1,000. So I'm going to say, and let's just write it this way, per one photon. So I'm going to say times 1 kilojoule over 1,000 joules. So that's kilojoules per photon. But how many photons are in a mole?
A billion.
No. How many donuts are in a mole? How many atoms are in a mole? 6.02 times 10 to the 23rd photons or electron transitions per 1 mole. And that's going to give you kilojoules per mole. Thank you, Jack, for doing this.
But is it times 10 to the 23rd?
Yes.
Okay.
Oh, the final answer? I don't know. I mean,
No,
but
I'm-
this is
I'm
6.02
asking for
times
that,
10 to the 23rd right there. So what you get?
I got 0.2395 or 96.
Kilojoules per mole. Okay? So that would be the energy in kilojoules per mole. So sometimes in these problems, you're given the energy in kilojoules per mole, but know that to put it into this equation, it has to be joules per photon. You would just do the reverse. You divide by Avogadro's number and multiply by 1,000. Set your units up so they cancel. Okay? So you just need to know the energy transitions on all that E equals H nu, all of these problems that you have to do. Sometimes you have to go kilojoules per mole. So you might want to look, I don't know if any of them ask for that on this particular sheet, but I'm stressing this today for a reason.
Would this be like an actual question or like a bonus question?
Actual question, because it's not hard. Okay? We good? I mean, it's just kilojoules and mole conversion.
What is the difference between the Planck's constant and the 6.02? Like, why do you use the 6 Planck instead of Planck's constant? Like, what is
Planck's constant is just what he found when he found that energy is related to the color or the frequency of the light. I mean, that was just a completely separate reaction equation, okay? It's just that the energy and frequency are directly proportional to one another, and whenever you have a direct proportion to change it to an equality, there has to be a constant. And, I mean, he figured out this relationship, and then Einstein took it and said that what he found was actually the energy of a photon. A mole is just a physical number, like a dozen is 12, a mole is just how much is present. But it takes that much to get a workable amount in chemistry because everything's so small.
Is it 6.02 on the equation sheet that you did?
Yes.
Okay,
Okay, but that's again, that's Avogadro's number. That's what we need. You know, that's how many atoms. When we have 18 grams of water, that's how many molecules of water are present. We have a mole of water. All right. So now that's all the major review that I felt like I needed to cover. So let's use the rest of the time to work on the Princeton review. And I'm going to put the ones that you need to know how to do on the board here. Let me go ahead and do that while people are on video. But it's pages 81 to 87 in your Princeton review.
Those part of it, okay.
81 to 87. So we're gonna go Princeton review. Pages 81 to 87. Multiple choice numbers 1 through 5. 7 through 9. 11. 13. 14. 16. 18 and 19. And then FRQs 1, 3, and 4. All right? That'll help you prepare as well for the test.
Where are the right answers?
And right at the end of the chapter.
Is this gonna be due like on Tuesday?
Yeah, I'll just check it, but I mean, your test is Monday, I'm not gonna be checking it on Monday. But look, it's stupid to do it on Monday night after you take the test, so get it done. All right. Thank you all, have a wonderful day, a wonderful weekend, and go Jags.
That's your outro?